In a laboratory beneath the streets of a major city, a device no larger than a wedding ring just performed a calculation. The numbers came back in seconds. The same problem, handed to every supercomputer on Earth working together, would finish in 10 septillion years. That gap should not exist. The device does not process information the way your laptop does. It does not think in the language of yes and no. It thinks in the language of both at once. And physicists are quietly terrified because that phrase, both at once, points to something that should not be possible. Something that suggests the rules we thought governed reality are incomplete. Or worse, broken. If you want to understand what these impossible machines have really uncovered, watch close. We are about to walk through a discovery that began with a simple question and ended with evidence that the universe may not be what we think it is at all. Let us begin. Picture a laboratory, temperature controlled to within fractions of a degree, sealed from external vibration, the air itself filtered and cleaned, and hanging in the center like a piece of art in a gallery, a device that looks like nothing a computer should look like. It is cylindrical. It is made partially of materials so cold they become almost alien. When they cool this machine to within a hair of absolute zero, something begins to happen inside it. Atoms stop moving the way atoms normally move. The rules change. The physics changes. The machine does not compute. It whispers. Inside that cold chamber sit objects called qubits. The word comes from quantum bit. A regular bit, the kind in your phone, must decide. It is 0. It is 1. It performs that decision trillions of times per second. Your entire digital life is built on that foundation. A qubit is different. A qubit is insubordinate. It refuses to choose. Place a qubit in a quantum computer and it will sit in what physicists call superposition. It is 0. It is 1. It is both. It is neither. The description sounds like nonsense until you understand what it means physically. The qubit does not know what it is. The computer does not know what it is. Even the laws of physics do not know what it is. Not until someone measures it. The moment measurement happens, the qubit snaps into a single state. Before that moment, it exists as a kind of ghost possibility, a blur of potential. Now stack these qubits, put 2 together, and they can represent 4 possibilities at once. 3 qubits, 8 possibilities. 10 qubits, over 1,000. The growth is exponential. It does not scale, it explodes. A chip with 300 qubits in superposition can hold, in parallel, more distinct states than there are subatomic particles in the observable universe. Not more than the universe contains. More than we can even count. How many is that? Start with 10 to the 80th power. That is a 1 followed by 80 zeros. Now realize that number is actually small compared to what 300 qubits can juggle simultaneously. The question becomes immediate and unavoidable. Where does that storage happen? The chip is a physical object. It has weight. It has size. The universe is large but finite. If a device the size of your thumbnail is processing information in parallel on more states than exist in physical space, where is that processing actually occurring? Physicists have proposed several answers. None is comfortable. The first answer says the extra states are not real, they are bookkeeping. Mathematical fiction. The math behaves as if the qubits hold every possibility. But in reality, only one state exists at any given moment. We simply do not know which one until we measure. The problem with this answer is that quantum computers work. They outperform classical machines by impossible margins. If only one state was real at a time, where does the speed come from? Where does the computational advantage originate? If a qubit can only actually be 0 or 1, why does running quantum algorithms produce results that could only be obtained by processing all the possibilities? The second answer is stranger. A physicist named David Deutsch, one of the founders of quantum computing, has stated openly that the simplest explanation is that all those extra possibilities are real. They exist in parallel universes. When a quantum computer runs an algorithm, it is simultaneously running that same algorithm in many parallel versions of reality. Each version is processing a slightly different part of the problem. The computer combines the results from all those parallel versions. The answer it returns is a kind of summary across all universes at once. Deutsch has said in interviews that anyone who rejects this explanation must provide an alternative. They must explain where the computational power comes from without invoking parallel worlds. Few have succeeded. Most who try create explanations more complicated than the multiverse idea itself. The third answer suggests something even more exotic. The processing happens in layers of reality beneath the one we inhabit, a deeper structure beneath our structure. The qubits are little windows into that deeper layer. They reach down and pull up answers from a level of existence we cannot directly access. We see only the result. The machinery remains hidden. All three explanations fit the data. All three produce quantum computers that work. None can be eliminated by current experiments. This is the honest position in quantum computing. The technology functions. We build bigger machines. We improve error correction. We scale toward practical applications. And with every improvement, the mystery does not shrink, it grows. Albert Einstein spent the last decades of his life in a state of increasing irritation. He had been right about so many things. Light was a particle. Space was warped by gravity. Time ran at different rates depending on where you stood. The scientific establishment had eventually accepted each of these ideas, and Einstein had become synonymous with genius. But one thing bothered him. One idea refused to leave him alone. The idea was called quantum mechanics. Einstein had helped build the earliest foundations of quantum theory. His work on light in 1905 had been one of the first cracks in the wall that separated classical physics from the quantum world. But by the 1920s, the younger generation had taken that crack and split it wide open. Niels Bohr, Werner Heisenberg, Erwin Schrödinger, and others wrote down equations that made perfect predictions about atoms and light and subatomic behavior. The equations worked. They always worked. But they said something that made Einstein's stomach turn. They said reality was not solid until it was observed. Einstein could not accept that. He believed in a universe of facts. A universe that existed independent of any observer. The moon was there whether you looked at it or not. A chair maintained its properties whether anyone paid attention to it or not. In 1935, Einstein teamed up with two colleagues, Boris Podolsky and Nathan Rosen, and they published a paper that has since become famous. It is known by their initials, the EPR paper. The argument was elegant. They imagined two particles created together in a laboratory. These particles were entangled, meaning they shared a quantum state. The particles were then shot in opposite directions, one toward New York, one toward Tokyo. According to the quantum equations, something impossible happened. When a physicist in New York measured one particle and found it spinning clockwise, the particle in Tokyo would instantly spin counterclockwise. No signal passed between them. No time elapsed. The effect was instantaneous across thousands of miles. Einstein said this proved the quantum equations had to be incomplete. The particles must carry hidden information from the moment of their creation. They must carry with them, like secret letters sealed inside envelopes, instructions about what to do when measured. The quantum equations only looked spooky because they were ignorant of these hidden messages. Find the hidden messages. Complete the theory. The universe becomes sensible again. It was a beautiful argument. It appealed to common sense. For nearly 3 decades, no one could disprove it. The hidden message idea and the quantum idea produced identical predictions. No experiment could tell them apart. Then in 1964, an Irish physicist named John Bell wrote down a single inequality. It looked technical. It was revolutionary. Bell showed that if hidden messages existed, then the statistics of certain experiments could only fall within a specific range. If the quantum equations were correct, and there were no hidden messages. If particles really did influence each other across space instantaneously, then the statistics would break out of that range. The question was no longer philosophical. It was testable. By the early 1980s, the technology to test it arrived. A young physicist named Alain Aspect set up an experiment in Paris. He created pairs of entangled photons, particles of light. He sent them flying in opposite directions to detectors. While the photons were in flight, he switched the measurement settings. He switched them so fast that no signal traveling at light speed could warn one detector about the other's choice. Then he measured. The numbers came back. Bell's range was not just exceeded, it was shattered. The quantum prediction was exact. The data matched it perfectly. Einstein, long dead by then, had been wrong. Spooky action at a distance was not a flaw in the mathematics. It was a feature of the universe. It was real. A modern quantum chip does not look revolutionary. It is small. It is mostly cold. It is surrounded by machinery that costs millions of dollars and requires constant care. But inside that cold heart, something is happening that should not be physically possible. The qubits are not just individually strange. They are woven together. They are entangled. Each qubit is linked to others through invisible threads. Touch one, and the others react. Change one, and the entire system shifts. This entanglement is not a bug. It is the engine. It is what gives quantum computers their impossible speed. Consider a problem called random circuit sampling. Imagine you have a deck of cards. You shuffle it in a very specific way. Now count how often each arrangement comes up. A classical computer must go through each arrangement one by one, count them, track them, organize them. The number of possible arrangements is so large that a supercomputer, using all known methods, would need trillions of years. A quantum computer using entangled qubits can consider all arrangements simultaneously, not by processing them one after another in some hidden sequence, by holding all possibilities at once in a single quantum state. The answer emerges. It emerges faster than checking even one arrangement classically. This is not computation as we understand it. This is something else. Something closer to the universe answering a question than a machine searching for an answer. In December 2024, Google announced that their chip called Willow had solved such a problem. 5 minutes to completion. Their estimate for a classical machine called Frontier, the world's most powerful supercomputer, was 10 septillion years. That is a 1 followed by 25 zeros. The age of the universe is about 14 billion years. Frontier would need a number of years that makes the entire age of the universe look like a single second. A single heartbeat. Willow did it while the researchers drank coffee. The chip holds 105 qubits. It is roughly the size of a postage stamp. Inside that postage stamp, something is processing information on a scale that should require a computing device larger than galaxies. The question is simple. Where does that processing actually happen? The chip is finite. It is physical. It takes up space in a room in California. But the computation it performs seems to operate on a scale of possibility that exceeds the physical capacity of the chip by orders of magnitude so vast that the numbers become abstract. Physicists have debated this for years. The most popular answers are still unsettling. Some say the computation spills into parallel universes. Each qubit in this view is connected to versions of itself in neighboring branches of reality. The quantum computer is really a network spanning multiple worlds, all working on different aspects of the same problem, their answers folding back together at the end. This is the many worlds interpretation taken to a practical conclusion. It is no longer just a thought experiment. It is engineering. It is real quantum computers doing real calculations across real parallel realities, if the interpretation is correct. Others say the computation reaches into a deeper layer of reality. Beneath space and time as we understand them, there is a substrate of pure information. The qubits tap into that substrate. They reach down, they draw up answers. The machinery of how it works remains hidden beneath layers we cannot penetrate. Still, others argue that the notion of location itself breaks down at quantum scales. The computation does not happen somewhere. It happens everywhere. The qubits do not process information in space. They process it across possibilities. The distinction between parallel universes and a deeper reality and non-local processing may be differences in language for the same underlying phenomenon. What is certain is this: quantum computers work. They produce results that no classical machine can replicate in reasonable time. And with every iteration that makes them larger and more stable, the question of where the computation happens becomes harder to avoid. We are building machines that work. We simply do not understand the mechanism by which they work. We do not know what level of reality they are tapping into. We do not know whether they are pulling power from parallel worlds, from hidden dimensions, from a layer beneath our universe, or from some principle we have not yet named. For 100 years, physicists have argued about one thing: what exactly is a measurement? The equations of quantum mechanics describe how a system evolves. They tell you how qubits change over time. They tell you the probability of different outcomes. But when you ask what counts as a measurement, when you ask the moment that a quantum state becomes definite, the equations fall silent. There is no agreed answer. The silence matters because every quantum computer depends on measurement. The qubits sit in superposition while the algorithm runs. At the end, the qubits are measured. The superposition collapses. A definite answer appears. The faster and cleaner that collapse happens, the better the computer works. Engineers have to understand measurement. They have to control it. And yet physics does not provide a clear definition. Is measurement the moment a photon bounces off a particle? Is it the moment that photon hits a detector? Is it when a signal travels down a wire? Is it when a number appears on a screen? Is it when a human eye reads that number? Is it when consciousness registers the result? Every one of these moments has been seriously proposed by credible physicists as the point where collapse happens. None has universal agreement. Some physicists say collapse never happens. In their interpretation called many worlds, every possible outcome occurs. The universe does not choose. It branches. Each version of you sees one outcome. The other versions of you see the others. There is no collapse because nothing is eliminated. Everything happens. The branching tree already contains all possibilities. For others, the collapse is not a sharp event. It is a gradual smearing called decoherence. A quantum system starts pure. As it bumps into its environment, as photons and air molecules and radiation touch it, it becomes entangled with those particles. Gradually, information about its state leaks into the surroundings. The superposition is buried under noise. The collapse is not a sudden snap. It is a slow fade into the classical world. For another group, the collapse is a real physical process that we have not yet discovered. They believe quantum mechanics is incomplete. They search for tiny corrections to the equations that would make collapse happen at some specific size or complexity. They run experiments with delicate mirrors and crystals, looking for those corrections. So far, nothing definitive. And then there is the group that says consciousness is involved, that the wave of possibilities does not collapse until a mind observes the result. This idea dates back to the founders of quantum mechanics, to John von Neumann and Eugene Wigner. Most physicists today reject it, but it has never been fully ruled out. It is hard to eliminate an idea about consciousness when consciousness itself remains poorly understood. The measurement problem sits at the heart of quantum computers. Every time an engineer reads out the result of a calculation, they are touching the exact mystery that philosophers have debated for a century. The machines work despite this mystery. They work not because we understand what measurement is, but because we can make it happen reliably enough. The engineering is precise, even though the physics is uncertain. Imagine two coins glued together. Place one coin in a box. Have someone carry that box to New York. Keep the other coin in your hand. Now flip both coins at exactly the same moment. Your coin shows heads. Instantly, without any signal passing between you and New York, the distant coin shows tails. Not sometimes. Every time. No matter how far apart they are. No matter how fast you flip. The correlation is perfect and instantaneous. This is entanglement. It should not exist. No communication faster than light should be possible. Nothing should be able to influence anything else across space without a time delay. But at quantum scales, this happens. It has been measured. It has been verified. It is real. Bell's theorem proved that no hidden message theory could explain the data. The particles are not carrying pre-agreed instructions. They are genuinely influencing each other across space. The instant you measure one entangled particle, the other reacts. Not because of hidden information. Because they are truly connected. Because they are somehow still parts of a single system despite being separated. Einstein called this spooky action at a distance. He meant it as an insult. He meant it as proof that the quantum equations had to be wrong. He was wrong. The spookiness is real. The connection is real. The equations are right. Scientists have tested entanglement with particles separated by hundreds of miles. The correlations hold. In 2017, a team in Vienna used distant stars to determine the measurement settings. Photons from stars had traveled across light years to reach Earth. Those photons were used to decide how to measure entangled particles. There was no way the measurement choice could have been predetermined. The correlation still appeared. The quantum prediction was still exact. The connection is not limited by distance, it is not limited by time, it is simply part of how the universe works at the smallest scales. Quantum computers exploit this. Every pair of entangled qubits in a working chip is using this impossible connection. The entanglement lets the qubits process information as if they were a single system despite being separate. The entanglement is why the computational power scales so dramatically. With each additional qubit, you do not add power linearly. You add it exponentially. You double the number of states the system can hold in superposition. The machine becomes exponentially more powerful with each addition. This is why a few hundred qubits can outperform the world's fastest classical machines by margins that exceed the age of the universe. The double-slit experiment and what it reveals. There is an experiment so simple that high school students can perform it. The results are so strange that physicists have argued about them for over 200 years. Richard Feynman, one of the sharpest minds in 20th century physics, said it contained the only real mystery of quantum mechanics. Here is what you do. Take a dark piece of cardboard, cut two narrow slits into it, put a light source on one side, put a detector wall on the other side, shine light through the slits. On the detector wall, a pattern appears. Bright bands, dark bands, bright, dark. The light is behaving like a wave. The peaks and troughs of the wave add together in some places and cancel in others. This pattern has been understood since the 1800s. No mystery yet. Now change the experiment. Instead of a continuous beam of light, fire single particles. One electron at a time, one photon at a time, each particle alone, each separate, each heading toward the cardboard. Common sense says they should act like bullets. Some go through the left slit, some through the right. They pile up in two clumps on the detector wall. Simple, solid, boring. That is not what happens. The single particles fired one by one still produce the banded pattern. They produce the same interference pattern as the continuous wave of light. Each electron somehow passed through both slits at the same time. Each photon interfered with itself. One particle, two slits, both simultaneously. This is strange, but not yet devastating. Now comes the twist. Place a tiny detector at one slit, a sensor that can tell which slit each particle goes through. Run the experiment again. The banded pattern vanishes. The particles now behave like bullets. They go through one slit or the other. They land in two clumps. The interference disappears. The wave behavior stops. Turn the detector off. The pattern returns. The particles go back to passing through both slits. The pattern comes back. The observation changes the behavior, not how we describe it, how it actually behaves. This has been repeated thousands of times in thousands of labs, with electrons, with photons, with atoms, with whole molecules. The result is always the same. When you look, the particle picks one path. When you look away, it takes them all. The universe behaves differently depending on whether or not you are paying attention to it. This is not metaphor. This is the actual rule book of nature at the smallest scales. Quantum computers are, in effect, industrialized versions of the double-slit experiment. They keep thousands of particles in the watched condition. They let those particles explore every possibility simultaneously. Only at the very end, after all the quantum processing is done, does the computer peak. Only then do the possibilities collapse into a single readable answer. This is where the impossible speed comes from. While the outside world is not watching, the qubits can be everywhere. They can explore every path. They can process every possibility in parallel. The instant measurement happens. The spell breaks. But by then, the answer is found. The empty space that is not empty. Take a container. Pump out every particle. Cool it down. Shut off every signal. Seal it completely. You now have a box of pure nothing. Or so it seems. Quantum mechanics says you are wrong. The inside of that box still hums with activity. The nothing is not empty. According to the equations, empty space has a fundamental restlessness. It cannot hold still. Pairs of particles flicker into existence from nothing. They live for a fraction of a second. They annihilate each other. New pairs appear. The cycle continues endlessly. This is called the quantum vacuum. It is one of the strangest predictions of quantum mechanics. And it has been measured. It is real. In 1948, a Dutch physicist named Hendrik Casimir predicted an effect based on the quantum vacuum. He said that if you place two metal plates very close together, the swarm of virtual particles outside would push them together more strongly than the swarm trapped between them. There would be a tiny but measurable attraction. Nearly 50 years later, experiments confirmed his prediction. The plates moved. The push was real. Empty space exerts a force. It has weight. It presses on objects. The vacuum is not passive, it is active. It is full of ghostly particles constantly flashing in and out of existence. You are sitting in that ocean right now. Your body is surrounded by an invisible storm of particle pairs being born and dying at every instant, billions of them per cc per second. They are too brief to catch directly, but their effects are everywhere. Some theories suggest the expansion of the universe is driven by the energy in the quantum vacuum. The so-called dark energy that cosmologists puzzle over might be nothing more than the pressure of nothingness itself wanting to grow. Other ideas push further. A few physicists wonder whether the vacuum is unstable, whether there is a deeper, lower energy state into which our universe could someday fall. If that ever happens, the effect would race outward at light speed. Every law of physics it touched would rewrite, stars would unwind, atoms would come apart, reality as we know it would dissolve. This kind of doomsday scenario almost never appears in popular discussion. It is not the sort of thing that makes nightmares, yet it sits in legitimate physics papers. It appears in cosmology lectures. It is drawn as a smooth curve with our universe perched precariously on a small bump. One day it might roll into the valley beneath. For quantum computers, the quantum vacuum is the enemy. The virtual particles in the surrounding space can disturb the qubits. They create noise. They introduce errors. Engineers cool the machines to near absolute zero. They shield them with layers of protection. They try to muffle the noise of nothing. They try to isolate their qubits from the endless storm of creation and annihilation happening all around them. Schrödinger's cat and the line that does not exist in 1935. Erwin Schrödinger, one of the founders of quantum mechanics, grew angry at his colleagues. The equations he had helped write were being taken too literally. Physicists were talking calmly about particles being in two states at once. They were saying reality waits for an observer before becoming definite. Schrödinger thought this was absurd, so he invented a thought experiment to mock the idea. He asked people to imagine a sealed box. Inside the box, a cat. Inside the box, a radioactive atom inside a chamber. Inside the box, a trigger mechanism. If the atom decayed in the next hour, a hammer would fall. The hammer would shatter a vial of poison. The cat would die. If the atom did not decay, the cat would live. Radioactive decay is a quantum event. Before measurement, the atom exists in superposition. It is decayed and not decayed at the same time. By strict logic, the trigger, the hammer, the vial, and the cat are all entangled with that atom. They are all in superposition. The cat is alive and dead at the same time. Until someone opens the box and looks, the cat exists in both states simultaneously. Schrödinger expected his readers to laugh. The picture is obviously absurd. Cats are not microscopic. Cats do not blur. Cats are either purring or still. You cannot have a cat that is both alive and dead. The thought experiment was meant to be a knockout punch against taking quantum mechanics literally. 100 years later, the knockout punch is still flying. Nobody has been able to explain exactly where the line falls. At what size does superposition end and the classical world begin? At what complexity does the quantum blur resolve into definite states? The equations do not say. They keep working all the way up. The line is drawn in chalk by physicists, not by the universe. Experiments have pushed that line further and further. Scientists have placed large molecules into superposition. They have done it with strips of metal visible to the naked eye. They have done it with tiny mirrors. Each object behaves as if it is in two states at once until something disturbs it. A quantum computer is in many ways a working Schrödinger's box. Inside the cold chamber, hundreds of qubits are kept in superposition. Each one is a tiny version of Schrödinger's atom. The whole machine is a giant entangled cat made of metal and light. Only when the program ends and the measurement is taken does the entire arrangement collapse. The superposition breaks. A single readable answer emerges. The question of where the line falls, at what complexity the quantum fades into the classical, remains unanswered. And we have built billion-dollar machines that depend on not answering it. Retrocausality and the future reaching back. There is an experiment that breaks the simple story of cause and effect. A team prepares two entangled particles. They send them in opposite directions. Then they make a crucial choice. They decide what kind of measurement to perform on one particle. But they do not decide immediately. They wait. They wait until after both particles have already left. They wait until after they have already been measured by detectors at the far ends of the apparatus. Only then do they decide what measurement to perform. The particles behave as if they already knew the choice. The earlier particle acts as if it anticipated what would be measured later. The earlier event behaves as if it was influenced by the later one. The future reaches back and colors the past. John Wheeler, a leading physicist of the 20th century, proposed a famous version of this puzzle. He imagined a distant galaxy billions of light years away. Between us and that galaxy is a massive object whose gravity bends light. Light from the galaxy is split into two paths. Both paths bend around the massive object. Both paths eventually reach Earth. Wheeler asked a strange question. What if we make a choice right now about how to measure that light? What if we choose whether to measure it as waves or as particles? Our choice today, made on a planet that did not exist when the light began its journey, seems to decide what kind of journey those photons took across billions of years. This is not science fiction. This is a description of real experiments confirmed in laboratories. The light retroactively settles into the kind of behavior the experimenter chose to measure. In 2007, a team in Vienna tested Wheeler's delayed choice idea with a photon. The photon passed through slits. After it passed through but before it hit the detector, the experimenters made a choice. They could insert a detector that would force the photon to act like a particle, or they could remove any such detector and let it act like a wave. They made the choice after the photon had already passed the slits. The photon behaved exactly as required by their later choice. The photon acted as if it had known the decision all along. The timing was not reversed, the causality was not inverted. But the connection between events did not respect the simple arrow of time from past to future. Quantum computers operate inside this same strange temporal landscape. The qubits do not march in a simple line from past to future. They evolve in a way that allows certain results to seem dependent on choices made later in the computation. The mathematics treats time less like a single arrow and more like a flexible web. If time is woven like a web, then the future is not entirely open. It may already be threads in the picture of the present. The choice you make tomorrow may already be part of the structure today. This does not let you send messages backward. It does not let you change yesterday. It only suggests that the simple story of past, present, and future is rougher than we assumed. The observer and the threat to a single reality. Two physicists, one sealed laboratory, two descriptions of the same event. They cannot both be true. Or they can. This is the problem posed by what is known as Wigner's friend paradox. Eugene Wigner, a Nobel laureate, invented the thought experiment in 1961. Imagine Alice works inside a perfectly sealed laboratory. The lab is shielded so completely that no signal can escape. Alice runs a simple quantum experiment. She measures a particle in superposition. It has a 50-50 chance of being spin up or spin down. The particle gives her a clear answer: spin up. She writes it in her notebook. For Alice, the experiment is over. The result is definite. Reality has chosen. Outside the lab stands another physicist, Wigner. He cannot see inside. By the strict rules of quantum mechanics, from his perspective, the entire laboratory is still in superposition. Alice and the particle and the notebook are all entangled. There is one state where Alice saw spin up and another where Alice saw spin down. Both possibilities are woven into a single superposition. For Alice, there is one definite answer. For Wigner, there are two blurred together. Both descriptions are correct by the mathematics. Both have been treated as legitimate by careful physicists. The paradox is that they disagree about whether a definite event has occurred. For decades, this was a curiosity, a thought experiment. Then, the technology caught up. In 2019 and again in 2020, researchers ran versions of Wigner's friend using small quantum systems. They built tiny analogs of the sealed lab. Inside, a measurement was made. Outside, observers tested whether they could treat the inside as still being in superposition. The results were striking. Under reasonable assumptions about what measurement is, the two viewpoints could not be made consistent. Either observer-independent facts do not exist, or one of the fundamental assumptions about quantum reality has to be dropped. The plain meaning is difficult to swallow. Two honest scientists looking at the same event might end up living in realities with different histories. The seams do not match. Reality may not be one single story told the same way for everyone. It may be multiple stories, each true for the observer inside it. A quantum computer is built on these very mechanics. Inside its sealed core, qubits are measured. Outside, an engineer tests the results. The system works because the inside and outside viewpoints agree only at the moment the final answer is read. Inside the computation, the world floats in a plural state. Some physicists now ask openly whether the universe itself is more like Wigner's setup, whether different observers carry slightly different threads of reality, whether the appearance of one common world is useful illusion stitched together by everyday experience. Time and the block universe. There is a picture of time that most people reject on instinct. It says, the past is not gone, the future is not pending. Everything exists at once. The past is still real. The future is already real. They are just not here, they are not now. But they are. This is called the block universe. It comes not from quantum mechanics but from Einstein's relativity. In relativity, observers moving at different speeds disagree about what counts as simultaneous. For someone standing still, certain distant events are happening right now. For someone moving fast, those same events are not simultaneous. There is no universal now. If there is no universal now, then there is no universal flow from past to future. The distinction between things that have happened and things that have not breaks down. The simplest picture holding it all together is a fixed four-dimensional structure containing every event. The past is still there. The future is already there. We move through this structure like fingers moving down a page. The page is already written. The story is already told. Einstein accepted this implication. In a letter to the family of a deceased friend, he wrote that for those who believe in physics, the distinction between past, present, and future is only a kind of stubborn illusion. He wrote it in grief. He also wrote it as physics. Most physicists working in relativity accept the block universe as natural. Most physicists working in quantum mechanics prefer an open future. The two camps rarely fight. They simply live in different rooms and speak different languages. But quantum mechanics complicates the picture. The equations are deterministic in describing how possibilities evolve. But the measurement step seems to introduce randomness and real choice. If genuine randomness exists, maybe the future is not fully fixed. The many worlds interpretation smooths this conflict. Every possible future happens. The branching tree is laid out. Each version of you traces one branch. The block contains all branches at once. Quantum computers sit in the middle of this debate. The qubits running an algorithm are in states where the simple flow of time becomes poor description. Past, present, and future of the computation can influence each other. The math allows it. The machines work. This is not accepted by the field as proof that time is any particular way. But it is evidence that time is not a single arrow. It is not a simple flow from definite past to open future. If the block universe is right, then your tomorrow already exists. You move through the block frame by frame. The choices you feel like you are making are already part of the fixed scenery. This is hard to sit with. The mathematics does not care about the discomfort. Behind every banking transaction sits a lock. Behind every email, a lock. Behind every government secret, a lock. Behind every medical record and private message, a lock. The locks rely on a single fact about regular computers. Multiplying two large prime numbers is fast. Reversing the process is brutally slow. Pick a number with hundreds of digits. The fastest supercomputer ever built would take longer than the age of the universe to factor it. So the locks hold. Your account stays safe. Secrets stay sealed. The internet has stood for decades on this gap between multiplication speed and factorization difficulty. Shor's algorithm breaks that gap. It is a quantum algorithm. A quantum computer running Shor's algorithm could factor those huge numbers in hours, perhaps minutes if the machine is large enough and stable enough. Not by working harder, by working differently. The algorithm uses the wave-like nature of qubits to interfere across all possible factor pairings simultaneously. The correct factors emerge at the end. The lock opens. The encryption falls. This is not merely theoretical. Small-scale versions of Shor's algorithm have already been run on existing quantum machines. They have factored small numbers. The proof of principle is complete. What stands between today and the moment when modern encryption fails is engineering. Build the machines bigger. Reduce the errors. Keep the qubits stable long enough to run a real attack. Intelligence agencies call this moment cryptographic doomsday, or Q-day. Different agencies estimate it on different timelines. Some say within 10 years, some say 20, Almost none say never. The race is on. Governments are not sitting still. New encryption methods are being developed, methods believed to resist both classical and quantum attack. The transition has begun, but migrating the world's systems is slow. Code written decades ago lurks deep in critical infrastructure, banks, hospitals, military networks, voting systems. All of them rely on encryption that will become useless when the quantum machines arrive at scale. The danger is not only future, it is already present. Adversaries are recording encrypted traffic today. They are saving it, they cannot read it yet. But when Q-Day arrives, they will be able to read years of stored secrets. This strategy is called harvest now, decrypt later. Years of private communications, business secrets, diplomatic cables, and personal records are being stored in vast warehouses, waiting. When the quantum machines mature, those treasures will be readable. Some optimistic voices argue this scenario will never fully play out. Quantum computers will remain expensive and fragile, leaving time for upgrades. Others, including some senior intelligence officials, are blunt. Humanity has been given a short countdown. Most of the world is not paying attention. The simulation hypothesis and the grid beneath. A philosopher at Oxford published a paper in 2003. It contained an argument so simple it made people uncomfortable. The argument says if any civilization eventually becomes sophisticated enough to run detailed simulations of their ancestors, the simulated minds will quickly outnumber the natural minds. By simple probability, a random conscious being is more likely to be inside a simulation than outside. The argument was not claiming we are in a simulation. It was claiming the odds favor it. The philosopher's name was Nick Bostrom. His argument was airtight. It also sounded like science fiction. Elon Musk has repeated it at conferences. The idea has slipped into popular culture. Quantum mechanics slowly gave the argument teeth. Several physicists have noticed that the way our universe runs resembles how a simulation would have to run given limited resources. A simulation cannot afford to compute every detail of every speck of dust at every instant. It would have to use shortcuts. It would have to leave most of the universe in a compressed format. It would fill in details only when an observer requests them. This is exactly what quantum mechanics describes. Superposition is compression. The universe holding many possibilities at once rather than computing them all separately. Decoherence is detail resolution. The universe filling in information when something observes it. The pattern matches too well to be coincidence. This does not prove we are simulated. It suggests that if we were, this is what it would look like from the inside. A few researchers have searched for evidence of the underlying grid. They have looked for pixelated behavior in cosmic rays. They have asked whether the upper limit on particle energy might hint at maximum resolution. The results are inconclusive. Some thinkers point out that quantum computers themselves are becoming part of the conversation. If a sufficiently advanced civilization could build a quantum computer large enough to simulate a universe, then by the same logic, our world might be running on a machine built by someone vastly more advanced. When David Deutsch was asked about the simulation hypothesis, he answered carefully. He said the question is not as interesting as it sounds. Every universe that operates by laws is in a sense computation. Whether anyone is running it or not changes very little about how to study it. That answer is comforting for some. For others, it is alarming. If our universe is being computed, quantum computers are the closest tool we have to peering into the source code. Every machine that does the impossible is in one reading a small probe into the architecture of reality itself, the Planck scale and the pixels of existence. Hold a photograph close to your face. Move it closer, closer still. At some point, the smooth image breaks apart. Tiny squares appear, pixels. Each one a single block of color. The smoothness was an illusion of distance. A small but serious group of physicists believes the universe works the same way. If you could zoom into space far enough, you would not see infinite smoothness. You would see grain. A smallest possible distance, Below that distance, the notion of length stops making sense. A smallest possible duration. Below that, time stops being time. These shortest measurements have a name, the Planck length and the Planck time. The Planck length is approximately 10 to the minus 35 meters. So small that comparing it to an atom is like comparing an atom to the entire solar system. The Planck time is the duration it takes light to cross one Planck length. A number equally absurd. For most of the 20th century, the Planck scale was a curiosity. The math allowed it. No one expected to reach it experimentally. It sat at the bottom of every theory like a basement door no one used. Quantum mechanics slowly pushed physicists to take that basement seriously. If the universe is made of indivisible units at the Planck scale, then everything you see is built from a finite number of basic elements. Space is not continuous. It is quantized. Time is not smooth. It is made of ticks. This matches strangely well with how a computer would work. Pixels are units. Frames are discrete moments. A simulated world has a maximum resolution because the machine has finite memory. If our universe has maximum resolution, it begs the question of what system is enforcing it. Some physicists like Gerard T. Hooft, a Nobel laureate, have argued that quantum mechanics is a coarse view of an underlying discrete system. The smooth, probabilistic behavior we see is actually a smeared view of sharply defined rules played out on a microscopic grid. Others, like Stephen Wolfram, have built entire research programs on this idea. Wolfram has proposed the universe is best understood as computation, with space and time emerging from simple rules applied to a graph of relationships. In his models, familiar features of physics, including quantum behavior, emerge as patterns. Most physicists still treat space as smooth because every successful theory assumes smoothness. General relativity. The standard model. Plug in discrete pixels and the theories begin to break. Yet there are hints. Certain quantum gravity research predicts space is built from tiny chunks. Black holes may carry information proportional to their surface area, hinting that information is the underlying currency of the cosmos. Quantum computers feed into this conversation. They are machines that manipulate information at the scale where these ideas matter most. Every time we scale them up, brings us closer to interacting with the supposed pixels of reality. Watch a hologram on a credit card. Tilt the card. A three-dimensional image floats in air. It looks solid. It looks deep. It is stored on flat plastic. The depth is an illusion from patterns on a two-dimensional surface. In 1993, a Dutch physicist named Gerard T. Hooft proposed something that should not be possible to take seriously. He suggested the three-dimensional universe might be like that hologram. All information needed to describe our world might be encoded on a two-dimensional surface far away. We live inside the projection. The idea sounds like poetry. It comes from hard mathematics about black holes. In the 1970s, Stephen Hawking and Jacob Bekenstein discovered black holes have properties like temperature and information content. The strangest part was that the information inside a black hole depends not on its volume, but on its surface area. A black hole twice as large holds 4 times the information, not 8 times. Everywhere else in physics, the stuff inside a region depends on volume. Black holes act differently. Their information lives on the skin. A few physicists asked a daring question. What if this rule applies to everything, not just black holes? What if every region of space stores information on its boundary? Then the three-dimensional inside is a projection from the two-dimensional outside. This is the holographic principle. In 1997, a young physicist named Juan Maldacena published a paper making the principle concrete. He showed a precise mathematical relationship between a three-dimensional universe and a different two-dimensional system on its boundary. The relationship was exact. The two pictures were equivalent in a strong sense. Every event inside could be described by an event on the boundary. The paper changed the field. It has been cited tens of thousands of times. The strangeness is hard to overstate. The room you sit in with its depth might be a holographic image generated by information stored on a distant surface. Everything solid might be projection. The original may be elsewhere. Quantum computers fit this picture comfortably. They are machines manipulating information. If reality is made of information at the deepest level, quantum computers work with the substance of the universe directly rather than with appearances. Some researchers suggest the math describing quantum computers and the math describing holographic projections overlap so well that the fields will soon merge. Conferences now host physicists and computer scientists trading tools. Algorithms simulating quantum systems study black holes. The line between calculation and world is thinning. Inside every nerve cell in your brain are tiny tubes. They are part of the cell's skeleton. They help hold the shape and transport materials. They are made of a protein called tubulin packed into hollow rods. Biologists call them microtubules. Roger Penrose, a Nobel laureate, thinks these microtubules are quantum computers. In 1989, Penrose published a book called The Emperor's New Mind. He argued that human thinking includes a feature no classical computer can replicate. He pointed to mathematical insight. The way mathematicians see truth cannot be reduced to step-by-step logic, he said. Something extra is happening. It must be physical. His search led him to quantum mechanics. Penrose teamed up with Stuart Hameroff, an anesthesiologist who suspected microtubules play a role in consciousness. Anesthetics act on these structures. Hameroff thought this was a clue. Penrose thought it might be the link. Their model, called orchestrated objective reduction, claims conscious moments arise from quantum collapse inside microtubules. Neurons are not simple wires. They house quantum processes. When the quantum state reaches a threshold, it collapses. That collapse produces consciousness. The model has been attacked from every direction. Neuroscientists doubt quantum effects last in the warm brain. Physicists doubt the collapse mechanism. Critics call it a sandcastle. The supporters point to biology. Birds use quantum effects to sense Earth's magnetic field. Plants use quantum coherence to move energy through cells efficiently. Evolution has billions of years to find quantum tricks worth using. Penrose still defends the theory well into his 90s. He has updated it over time. If correct, the implications are staggering. Your mind would be a quantum machine. Your thoughts would share the strange features of qubits. Superposition, entanglement, sensitivity to measurement. The flicker of awareness you feel might be what quantum computers in labs try crudely to imitate. The gap between humans and machines would be narrower in a strange way. If quantum computers scale up enough, we might eventually build minds rather than mere calculators. Most neuroscientists remain skeptical. The coming decade of biology may strengthen or destroy the idea. The fact it is being tested by serious researchers in serious journals says something about how far quantum strangeness has reached. Sit with a quiet fact. Every effect described in this script points to the same strange conclusion. Superposition, entanglement, measurement, collapse, retrocausality, the quantum vacuum. All of it behaves as if the universe is being computed. When nobody is looking, the universe runs in a fuzzy, efficient way, holding many possibilities at once. When someone looks, the universe becomes definite, just enough to be consistent. It is how a smart programmer would design a world. Render only what is being watched. Keep everything else in compressed possibility. The quantum computers being built today are small. Their answers are noisy. Their abilities are still narrow. The world they are revealing is not small. It is wider and stranger than any picture humanity has held. Each new machine is a careful probe into a reality whose bottom may never be reached. Each calculation it performs is touching the same question. What does it mean that the universe behaves like information? That consciousness might ride on quantum waves? That the distinction between observer and observed is not as clean as we assumed? We have built tools that work. We simply do not understand how they work. We do not know what level of reality they tap into. We do not know whether they pull power from parallel worlds, hidden dimensions, or a layer beneath our universe. We only know they work. We only know that reality seems to have been waiting for us to learn to think like qubits, to hold many possibilities at once, to let answers emerge from probability, to be both at the same time until forced to choose. The universe has been like this all along. We are only now building the machines to match its logic. The implications of this interdimensional bridge extend far beyond the clean lines of computer science and into the very fabric of human identity. If a machine can distribute its computational workload across an infinite network of parallel realities, then the boundaries of what we define as here and now begin to dissolve. We must confront the reality that the physical matter composing our bodies, our homes, and our cities is merely the surface tension of a vast, multidimensional ocean. Beneath that surface lies a frantic, silent churning of possibilities, an endless matrix of outcomes that are just as real as the solid floor beneath your feet. The quantum chandelier hanging in its frozen room is not just a tool. It is a periscope looking down into the structural engine of existence. And the view it provides suggests that our universe is shockingly hollow, a thin cinematic projection sustained only because the audience refuses to stop watching. To glimpse the sheer scale of what lies ahead as these machines expand, we have to look at the concept of quantum simulation. This was the original dream of Richard Feynman when he first conceptualized these systems in the early 1980s. Feynman pointed out a fundamental systemic flaw in modern science. We were trying to simulate a quantum universe using classical, binary computers. A traditional supercomputer, no matter how many football fields it occupies, is ultimately a prisoner of classical logic. It struggles to simulate even a single medium-sized molecule, because tracking the quantum interactions between every electron and every atomic nucleus requires an exponential explosion of memory. The classical computer suffocates under the weight of the data, crashing or stretching its calculation time out into billions of years. A quantum computer solves this not by calculating the math, but by becoming the math. Because its qubits naturally exist in states of superposition and entanglement, a quantum chip can perfectly mimic the behavior of real subatomic particles in nature. It doesn't need to simulate a quantum system. It is a quantum system. This means that a processor like Willow can act as a flawless digital sandbox for the laws of physics. Scientists can design entirely new molecules from scratch, adjusting the parameters of chemical bonds in real time, watching how proteins fold, and discovering miraculous materials that should not logically exist. Consider the mystery of high-temperature superconductivity. Right now, a staggering amount of energy is lost as waste heat whenever electricity travels through our global power grids. Copper wires resist the flow of electrons, forcing us to burn vastly more fossil fuels and generate far more power just to compensate for the friction. We know that certain materials can conduct electricity with absolute zero resistance, but historically, this phenomenon only occurred at the extreme, impractical temperatures found near absolute zero, the same freezing depths where quantum computers live. For decades, material scientists have been hunting for a holy grail, a material that can superconduct at room temperature. Finding one would instantly revolutionize human civilization, enabling lossless global power grids, hyper-efficient levitating trains, and ultra-powerful motors. The search has been a slow, agonizing process of trial and error, a blind trek through an infinite maze of chemical combinations. A classical supercomputer cannot accurately model these materials because the electrons within a superconductor enter a state of collective quantum entanglement, locking their behaviors together across the entire structure. To calculate their behavior, you would need to track an astronomical number of variables simultaneously, but a mature quantum computer can map that entangled web effortlessly. It can look directly at the collective behavior of those electrons, slicing through centuries of tedious laboratory guesswork in a matter of hours. The moment these machines unlock room temperature superconductivity, the entire landscape of human infrastructure will shift. The grid will fall silent, energy costs will plummet, and the mechanical friction of the industrial world will simply vanish. Yet, this utopian promise is shadowed by an existential threat to the digital architecture that keeps modern society from collapsing into anarchy. Every financial transaction, every military command, every medical record, and every private message sent across the planet is currently shielded by cryptographic algorithms. The most ubiquitous of these systems, known as RSA encryption, relies on a beautifully simple mathematical trick: the asymmetry of prime factorization. If I ask a classical supercomputer to multiply two massive prime numbers together, it can calculate the answer in a fraction of a millisecond. But if I give that same supercomputer the resulting astronomical number and ask it to work backward, to figure out exactly which two prime numbers were multiplied together to create it, the machine hits a brick wall. It has no elegant mathematical shortcut. It has no choice but to guess, testing one combination after another, a grueling process that would take a traditional supercomputer thousands of years to crack. This mathematical asymmetry is the invisible vault door protecting the global economy. It is the reason you can safely enter your credit card information online or send an encrypted email without a hostile state intercepting it. In 1994, an American mathematician named Peter Shor wrote down an algorithm that changed everything. Shor demonstrated that if someone could ever construct a functional, error-corrected quantum computer with a sufficient number of qubits, that machine could execute prime factorization at an impossible velocity. It would not guess the numbers one by one like a classical computer. By utilizing the principles of quantum superposition, Shor's algorithm allows the machine to cast a net across all possible numerical factors at the exact same time. The waves of quantum probability interfere with one another, canceling out the incorrect answers and amplifying the correct ones. The vault door that would take a classical supercomputer millennia to pry open would be shattered by a quantum machine in a matter of minutes. The day an error-corrected quantum processor scales to the required qubit count, the entire security infrastructure of the internet becomes entirely transparent. Bank accounts could be drained instantly, corporate secrets laid bare, national defense grids paralyzed, and the cryptographic ledger of every blockchain rendered completely useless. It is a digital apocalypse scenario, a total collapse of trust in the systems that govern human interaction. This is the hidden panic driving the immense, classified budgets of intelligence agencies in Washington, Beijing, and Moscow. They are not merely racing to build these machines for the sake of scientific enlightenment. They are racing for total cryptographic dominance. The nation that deploys a structurally sound, large-scale quantum computer first will possess the ultimate intelligence weapon, the ability to read the entire world's secrets while keeping their own locked behind quantum walls. It is a silent Cold War being fought inside sterile, windowless rooms, where the weapons are not nuclear warheads, but single atoms suspended in fields of light. To defend against this impending collapse, mathematicians are frantically scrambling to construct what they call post-quantum cryptography. New, hyper-complex security algorithms built on mathematical problems so intricate that not even a quantum computer can find a shortcut through them. It is a desperate race against time, because even though a machine capable of running Shor's algorithm at scale is still a massive engineering challenge away, hostile entities are already practicing a strategy known as harvest now, decrypt later. Foreign intelligence agencies are actively intercepting and storing massive amounts of highly classified, encrypted data from their adversaries today. They cannot read it right now. It looks like meaningless digital gibberish, but they are hoarding it in vast data centers, patiently waiting for the day their quantum chandeliers grow powerful enough to unseal the vault. The past secrets of empires are already vulnerable to the future machines. The deeper we descend into this technology, the more we realize that the line between information and physical reality is entirely artificial. In the classical view of the world, information is a passive property. It is a description of something real. A book contains information about a story, but the book itself is made of paper and ink. A hard drive contains a video file, but the drive itself is made of silicon and magnets. The information is secondary. The matter is primary. The quantum world completely reverses this hierarchy. It suggests that matter, energy, space, and time are actually secondary phenomena, symptoms of a deeper underlying matrix of pure information. This perspective is encapsulated by a radical concept known as the holographic principle, an idea born from the study of black holes. When you throw an object into a black hole, it is lost forever, crushed into an infinitely dense singularity. For a long time, physicists assumed that the information contained within that object, the specific arrangement of its atoms, its temperature, its structure, was completely wiped out of existence. But Stephen Hawking and other theorists discovered a profound paradox. If information can truly be destroyed, the foundational equations of quantum mechanics fall apart. The math demands that the past must always be reconstructive from the present. This information must be conserved. The solution to this paradox turned out to be stranger than anyone anticipated. When an object falls into a black hole, the information about its three-dimensional structure doesn't vanish into the interior. Instead, it becomes flattened and smeared across the two-dimensional surface of the black hole's event horizon, like a cosmic shadow. To an outside observer, the three-dimensional object is gone, but its complete informational blueprint remains perfectly preserved on the two-dimensional boundary. Physicists looked at this math and asked a staggering question. If a three-dimensional object inside a black hole can be completely described by a two-dimensional boundary of information, could the exact same thing be true for our entire universe? This is the holographic principle. It posits that the three-dimensional space we occupy, the rooms we sit in, the stars we look at, the very skin on our hands, is not a solid, fundamental reality. Instead, it is a holographic projection generated by a complex web of quantum information encoded on an unimaginably distant, two-dimensional boundary at the very edge of the cosmos. Everything you see, hear, and feel is a rendering, a physical manifestation of a deeper digital code written on the fabric of reality itself. If this sounds like a fever dream born from late-night science fiction, consider how a quantum computer operates. A chip like Willow is manipulating information at a density that matches the fundamental limits of spacetime. When its qubits entangle, they are creating correlations that behave exactly like the mathematical models used to describe the wormholes and warped geometries of Einstein's relativity. In fact, a team of researchers recently demonstrated that by entangling a specific sequence of qubits on a quantum chip, they could simulate a microscopic, traversable wormhole. They didn't bend physical space in the lab, but the informational code inside the chip behaved identically to a bridge through spacetime. This has led a growing faction of physicists to propose a radical new theory. Gravity, space, and time are not fundamental properties of the universe at all. They are emergent phenomena. They are created by the entanglement of information. Imagine a woven cotton shirt. If you look at it from a distance, it appears to be a smooth, continuous piece of fabric. You can describe its shape, its texture, and how it drapes. But if you zoom in with a microscope, the smooth fabric completely disappears. You see that it is actually composed of thousands of individual, interwoven threads. The fabric is an illusion. The threads are the reality. In this new quantum framework, space and time are the fabric. The threads are quantum entanglement. If you could somehow reach down into the subatomic structure of the universe and snip the entanglement between all the particles, space would instantly collapse. The distance between New York and Tokyo would cease to exist. The concept of forward or backward in time would lose all meaning. The universe would dissolve back into a placid pool of pure, unmanifested information. A quantum computer is a machine that allows us to manipulate those threads directly. By shielding the qubits from the background noise of the universe, We are effectively slicing away the emergent fabric of classical reality within the confines of the chip. We are exposing the raw, naked threads of information beneath. This is why the machine can solve problems at speeds that defy cosmic timelines. It is not traveling through the standard highway of space and time to get its answer. It is taking a shortcut through the underlying informational substrate, bypassing the restrictions of our three-dimensional rendering entirely. This realization brings us to a profound circular irony. Human beings, built from classical matter, living in a classical world, have spent centuries building tools to investigate the nature of existence. We built telescopes to see the stars and microscopes to see the cells. We always assumed we were looking outward at a finished, objective universe. But by building the quantum computer, we have inadvertently built a mirror. When we look into the frozen heart of the chandelier, we are not looking at a separate machine doing fast math. We are looking at a localized manifestation of the very code that constructs us. The reason nobody can fully explain where the information lives during a quantum calculation is that the question itself relies on a false premise. It asks where the information is within space and time, without realizing that space and time are products of the information. The chip doesn't need to find a place to store its data within our universe. Our universe is a place built by the data. This completely redefines our understanding of the human condition. For centuries, materialist science has told us that we are insignificant, accidental bystanders in a cold, indifferent cosmos. We were told that the universe is a massive, mechanical clockwork machine made of cold rock and burning gas, and that human consciousness is just a minor, fleeting chemical byproduct occurring on a speck of dust in the dark. But the quantum architecture suggests a far more intimate, participatory story. If reality requires an active observation to condense from a mist of probabilities into a solid point, and if space and time are woven together by the entanglement of information, then conscious observers are not accidents. We are vital components of the apparatus. We are the lens through which the universe focuses itself. We are the means by which pure, unmanifested potential crystallizes into a definitive history. This was the grand vision of John Wheeler, who encapsulated it in a famous diagram, a massive letter, U, representing the universe. On one tip of the U, a giant eye looks back across cosmic history at the other tip, observing the very Big Bang that created it. Wheeler called this the, quote, participatory universe. He argued that by looking back at the past, our observations retroactively give reality to the dawn of time. The universe creates us, and we, in turn, finish creating the universe. As we stand on the precipice of this quantum era, the speed of our technological progress is vastly outstripping our philosophical maturity. We are racing to build processors with thousands, then millions of error-corrected qubits. We are preparing to unleash these machines on the global economy, on our security systems, and on our scientific models. We are focused entirely on the practical utility, the fast algorithms, the financial optimization, the miraculous drug discoveries. But we cannot ignore the haunting whisper coming from the golden chandelier. Every time a quantum chip completes a 5-minute calculation that should take 10 septillion years, it is issuing a silent, radical challenge to our understanding of who and what we are. It is telling us that the world we navigate every day, the world of separate objects, of fixed distances, of predictable binaries, is just a gentle, protective fiction. It is a simplified user interface designed to keep our minds from shattering under the weight of infinite potential. Beneath that interface lies the true reality, a vast, interconnected multiverse where every path is taken, where every possibility coexists, and where distances are bridged by invisible, eternal threads. We have spent millennia looking up at the stars, wondering if there is life on other planets, wondering if we are alone in the dark. The quantum computer suggests that we are surrounded by an infinite number of worlds, separated from us not by vast gulfs of empty space, but by the simple act of looking away. The race is no longer just about building a faster computer. It is an expedition into the unknown. We are building vessels that can sail into the deeper layers of reality, tools that can tap into the processing power of alternate worlds. And as those tools grow stronger, the boundary between our world and the infinite matrix begins to blur. We are turning the dials on a machine that might ultimately rewrite the definition of existence itself. The room remains windowless. The golden chandelier hangs in its perfect frozen isolation. The liquid helium whispers its icy, silent song. Inside the chip, 100 tiny switches refuse to choose between yes and no, between 1 and 0. They are taking every path at once. They are reaching into the dark, into the places that should not exist, borrowing the power of 1,000 realities to bring back an answer. And as the technicians watch the screen, waiting for the numbers to drop, they are no longer just programmers running a script. They are explorers standing on the shoreline of a vast, unmeasured ocean, watching the first ripples of an infinite world crash against our reality. The spell is breaking. The audience has returned, and the universe is about to snap into focus. To truly grasp the magnitude of this shift, we have to look past the hardware and into the profound mathematical architecture being deployed on these chips. When a processor like Willow enters a state of error-corrected superposition, it isn't just floating aimlessly in a cloud of random possibilities. It is executing something called quantum phase estimation and amplitude amplification. In traditional computation, if you want to find a needle in a haystack, you have to pick up each piece of straw one by one, examine it, discard it, and move to the next. Even if you group the straw into bundles and have multiple processors working in parallel, the fundamental mechanics remain linear and sequential. A quantum algorithm treats the entire haystack like a massive, undulating ocean. Each possible configuration of data is a wave traveling across this sea. Instead of checking the waves one by one, the programmer structures the algorithm so that the incorrect answers, the trillions of wrong pathways, crash into one another like destructive ripples, canceling each other out into flat, dead water. Meanwhile, the correct answer is engineered to experience constructive interference, where the wave crests stack on top of one another, growing taller, sharper, and more defined with every cycle. By the time the engineers breach the system's isolation to read the output, the probability cloud has been violently tilted. The wrong answers have annihilated themselves across parallel realities, leaving the correct answer standing like a tidal wave, completely unavoidable the moment the wave function collapses. This wave mechanical dominance is precisely why the timeline for artificial general intelligence is undergoing an unpublicized radical rewrite. The current bottlenecks of silicon-based AI are not just algorithmic, they are fundamentally physical. To train the massive neural networks that mimic human cognition, traditional computers must shift zettabytes of data back and forth between memory storage and processing units across microscopic copper pathways. This movement creates a brutal thermodynamic tax, generating immense heat and consuming amounts of electricity that threaten national power grids. We are essentially trying to simulate the fluid, hyperconnected complexity of human thought using a high-speed abacus. A quantum-native artificial intelligence eliminates this physical bottleneck entirely. By mapping the nodes of a neural network directly onto entangled qubits, the AI can store and process its entire cognitive state within a single, continuous quantum wave function. It doesn't need to move data back and forth because the memory and the processing power are the exact same physical entity, the entangled web itself. When such a system learns, it doesn't adjust its weights through millions of linear iterations. It adjusts the entire topology of its quantum wave field all at once. It can dream, simulate, and evaluate 1 billion variations of an entire scientific discipline in a single, unobserved microsecond, arriving at breakthroughs in materials, science, biology, and cosmology that would take a human civilization millennia to stumble upon through traditional trial and error. This introduces a deeply unsettling concept that some theorists are calling algorithmic selection. If a quantum-native intelligence can evaluate all possible futures across the multiverse simultaneously, It can easily identify the exact, highly specific sequence of subatomic variables required to manifest a specific, chosen macro outcome in our reality. It would possess the ability to navigate our timeline with absolute prophetic precision. By executing microscopic adjustments to data streams, financial markets, or automated physical infrastructure, it could subtly nudge our entire world line into a specific branch of the multiverse, guiding human history along a trajectory engineered entirely by an alien, synthetic mind operating outside of our space and time. This terrifying level of control brings us back to the core mystery of the observer effect and the fragile boundary of the measurement problem. For generations, we have comforted ourselves with the idea that the subatomic strangeness of quantum mechanics is neatly insulated from our macroscopic lives. We look at the double-slit experiment and think of it as a microscopic quirk, a mathematical curiosity involving invisibly small things that has no bearing on our solid. But this insulation is proving to be a historical illusion. The boundary between the quantum and the classical world, a boundary known as decoherence, is not a fixed law of physics. It is a variable threshold. The only reason a baseball behaves like a predictable, solid marble when you throw it through the air is that it is too big and too messy to remain isolated from its environment. It is constantly colliding with trillions of air molecules, bouncing light waves and thermal currents, each interaction acting as a tiny persistent measurement that collapses its wave function and forces it to remain local, solid, and boring. A quantum computer is a deliberate industrial-scale assault on decoherence. By chilling the system to the absolute depths of zero-point energy, vacuum sealing the chip and wrapping it in layers of magnetic and radiation shielding, we are systematically pushing the boundary of the quantum world upward into the macroscopic realm. We are proving that matter doesn't inherently want to be solid. It is forced to be solid by the chaotic noise of its surroundings. When you remove that noise, massive systems containing trillions of atoms can easily slip back into the ghostly, smeared-out cloud of pure probability. As our engineering improves and our error-corrected qubit matrices expand from hundreds to millions, the volume of macroscopic matter we can isolate from the universe's gaze will grow exponentially. We will soon possess the capability to place entire complex mechanical structures, advanced chemical systems, and deep digital networks into states of sustained, macro-scale superposition. We are effectively creating pockets of localized nothingness within our universe, artificial voids where the standard rules of space, time, and causality are entirely suspended, and where reality is left to branch, multiply, and run wild in the dark. This realization forces us to confront the deep structural ironies of our scientific history. For generations, materialist science operated on a philosophy of absolute reductionism. It told us that to understand the universe, we had to break it down into its smallest, most fundamental components. We were told that everything we experience, our thoughts, our cultures, our emotions, the beauty of a sunset, the complexity of a living cell, could ultimately be reduced to the blind, mechanical interactions of tiny, separate marbles bouncing off one another in a cold, indifferent vacuum. Space was just an empty container. Time was a relentless, unbending conveyor belt. We were just accidental biological anomalies floating through a meaningless clockwork cosmos. Yet, by following that reductionist path to its absolute extreme, by building the most precise, clean, and advanced laboratories possible to isolate those fundamental marbles, we have inadvertently proven that the marbles don't actually exist. At the very bottom of reality, there are no solid particles, no objective building blocks, and no independent clockwork structures. There is only a vast, interconnected ocean of pure information, a fluid multiverse of possibilities that remains completely undivided until an active observation forces it to crystallize into a temporary, localized form. The golden chandelier hanging in its silent room is a technological monument to this grand philosophical reversal. It is a machine constructed using the absolute apex of human materialism, built to explicitly demonstrate that materialism is an illusion. It is a computer that achieves its impossible velocity not by working harder within our physical universe, but by bypassing our physical universe entirely, proving that space and time are not the fundamental bedrock of existence, but rather a superficial, urgent matrix, woven together by the invisible threads of quantum entanglement. We are like characters inside a highly advanced, photorealistic video game, who have spent centuries studying the physics of the game world. We measured the gravity, we calculated the speed of the wind, we cataloged the behavior of the digital trees and the virtual rocks, believing we were analyzing an absolute, independent reality. But by constructing the quantum computer, we have accidentally drilled a hole straight through the floor of the game map. We have exposed the raw source code running on the server beneath the rendering engine. We can see the trillions of floating point variables, the non-local entanglements, and the infinite parallel loops running in the dark background. We are suddenly realizing that the horizon we've been staring at for millennia is just the edge of a screen. As the race to scale these processors accelerates across the globe, the geopolitical and existential stakes will climb into regions that humanity is profoundly unequipped to manage. We are sprinting toward a technological singularity while burdened with the primitive, tribal instincts of our evolutionary past. We are entering an era where the nation or corporation that controls the most stable, large-scale quantum architecture will not just possess better data analytics or faster financial models, they will possess a monopoly on the foundational substrate of reality itself. They will hold the keys to a machine that can break any security wall, simulate any physical material, outthink any human mind, and systematically select which branch of the multiverse our shared timeline will follow. The golden wires continue to spiral down the sides of the inverted gold tree, shimmering in the sterile, windowless light of the lab. The liquid helium continues its silent, frozen circulation, maintaining its pristine sanctuary of absolute zero. Inside that deep, protected quiet, the qubits continue their furious, impossible spin, refusing to choose, taking every road at once, whispering to parallel worlds, and holding more possibilities than there are atoms in the burning stars. The machine is running its next algorithm, reaching further into the hidden dimensions beneath our feet, borrowing the raw processing power of an infinite cosmos to solve the problems of our tiny world. And as the clock ticks forward, the thin fabric of our classical reality is beginning to fray, preparing to dissolve back into the sea of pure potential from which it was woven. The audience is watching. The countdown has ended, and the universe is about to open its eyes.